All right, practice exam key. So, a couple nomenclature questions. Basically, the first thing you gotta do is find the parent name. Pentane is 5. So 1, 2, 3, 4, 5. Then substituents off that ring, or off that, not that ring, it's not a ring, the straight chain. 3 ethyl, 1, 2, 3. 2 carbons is ethyl. 1 carb on carbon 2 is chloro. So 2 chloro, 3 ethyl pentane. This one, it's a ring, right? And it's 6, so it's cyclohexane. There's 4 methyls off of it. 1, 2, 3, 4. All right, so it's a tetramethyl. And which carbons are those on? 1, 1, 3, 3. 1, 1, 3, 3. Tetramethyl cyclohexane. That one. Correct. This is again N-ethylpropanamine. Got to know propanamine means how many carbons? 3 carbons with nitrogen. 1, 2, 3. So there's your parent name. N-ethyl means there's an ethyl off the nitrogen as well. There's your answer. Make sure in these multiple choice questions, such as these, try to make your own answer first and then go look for it. Correct chair structure.
Hang on that one again.
All right, so this one, wedge and dashed, trying to convert it to a chair. So again, I like to look at this. I see this ethyl piece is wedged, so I think of it as up. The methyl and the bromine are both dashed, so I think of those as down, right? So I think of those as down. So I'm looking for something that has, now I gotta be careful and make sure, right? Notice these are on what the bonding matters too. Don't get confused, right? This is 1, 2, 3, 4, 5, 6. Make sure they're in the right spots. So for this one, I need the ethyl up. Bromine's up here, no. Ethyl's up, methyl's up, no. This one has them all down. And so this one has the ethyl up, bromine down, and the methyl down. So equatorial down, axial up. That's one that matches for this one. I got a couple people in this one. How many hydrogens in the molecule? Places where people missed. They didn't realize this is really a CH3 out here, or they forgot there's an H here, or there's 2 H's here. All right, so the answer should have been 10. So, careful with those hidden hydrogens, understanding those things. Just be, slow down, take your time, you have time. This one, orbital overlap, again, these are the kind of questions we've asked quite a bit. This one, oxygen and carbon, so the oxygen and carbon. So first you gotta figure the hybridization state of each. They're both sp2 hybridized because they have 1 pi bond. If they're sp2 hybridized, they use sp2 hybrid orbitals to make single bonds, so the answer is D. Add in lone pairs and informal charges. Assume all atoms have full octets. So make sure you, assuming things have full octets. So you'll have a periodic table tomorrow. Make sure you're thinking with that. Sulfur wants to have 2 bonds, so then it has 2 lone pairs. Oxygen wants to have 2 bonds, but here it has 3. That should clue you in that it has a plus charge and a lone pair, right? Because I said assume everybody has a full octet. Lone pair, sulfur 3 bonds, oxygen with 2 bonds, 2 lone pairs. So, thinking about what you know from the periodic table and all those things. Draw curved arrows, right? So those are the arrows we draw. This is like a bonds broken, bonds formed type thing. We did this a lot, right? Sulfur, you make a sulfur hydrogen bond. So the lone pairs go and go to the H and make a new sulfur hydrogen bond. The OH bond breaks. Those electrons go to the oxygen, right? 2 electrons in a bond, right? So that's what these arrows are showing. This term electrophile and nucleophile, so nucleophiles are electron rich, right? Things that are electron rich. That is going to be a nucleophile. That's where the arrows start, right? People where it's electron rich, and that first arrow is going to end where it's electron deficient. That's the electrophile, electron poor. So the H is the electrophile. We'll talk more about those terms, but you know the terms electron rich and electron poor. Okay, so let's do conformation of Newman projection. So this is another way the Newman projection works. So we got a wedge and dash structure. And of course, if you were standing here looking, right, you'd have 2 things you have one thing at your, what do we got here? One thing at your feet, one thing at your head, right? So what do you see? You see bromine down, and so you have an H and a CH3. This is a CH3. Chlorine is up, so this is a staggered conformation. OH is also dashed on the same side as the H. This H and this methyl on the same side here, so you get to that first spot. Good. Once you get there, right? So maybe you goof that up. I don't know. It doesn't matter. I start to grade you from here. Carbon 2 counterclockwise, so 1 and 2. So that means we're rotating 2. But the first one carbon doesn't change in any of these. So whatever one is not rotating, you don't touch it. You set it and you forget it. 60 degrees means you go from, if you start at staggered, you go to eclipsed, or if you start at eclipsed, you go to staggered. So 60 degrees, rotating carbon 2 counterclockwise, we're going this way. So chlorine's going to now be eclipsed with H, OH with Br, and then CH3, or the H now with the CH3. Staggered to eclipsed. We're going to do another 60 degrees. So now we're eclipsed, we're going to go to staggered. Again, the front one doesn't change. Chlorine goes here, OH here, H here. Now to staggered. One more rotation, why not? Now we're from staggered back to eclipsed. Everybody's lined up. And then, you know, whatever you have in D, then you need to turn that into a Newman projection with wedges and the dashes. So now you look at this and you say, okay, well, if I'm looking down here at this, I have two things at my feet. So this is an eclipse conformation. CH3 and OH are on my right, coming out at me, and the two H's are going away. All right, some resonance. I'll give you more space than I did here. This is my bad. Again, though, what we're thinking about, lone pairs, where we start resonance, make a pi bond breaks, lone pairs go to an atom. Right? If we start with lone pairs, usually end of the lone pairs on an atom. Right? So lone pairs, pi bond, new pi bond, carbanion. Carbanion makes new pi bond breaks, carbanion. Lone pairs make a pi bond breaks, carbanion. Carbanion makes pi bond breaks, O minus. Right? So biggest thing here is keeping track, adding your lone pairs, being careful with your arrow placements. Right? If you're making a pi bond, the arrow needs to go between two atoms. If electrons are going to an atom, the arrow needs to go to an atom, so I gotta give you space to show that. All right, draw the mechanism arrows on the starting materials. So starting materials, left side, to form product. Will the starting material or products be favored in this equilibrium reaction? Okay, briefly explain your reasoning. So if we're gonna explain this, so first you gotta know bonds broken, bonds formed. You could add in lone pairs, why not? I mean, it never hurts to like do the things correctly. All right. Electron density, right? Negative charge lone pairs is going to add into the carbon here. It's going to break the pi bond. The pi bond electrons are going to go to the oxygen. It's going to have a lone pair there. That's why it has a negative charge, 3 lone pairs. It adds in there. And then what's more favored, first you want to look at what's the octet rule. So does everybody have a full octet, right? That's usually the first thing we ask. Does everybody have a full octet? Everybody has a full octet, okay. And then we're going to look at O minus versus N minus. That's the major difference, what atom's charged. And because oxygen and nitrogen are both in the same row, it's about electronegativity, and oxygen's more electronegative. So it's going to be more stable because it wants electrons more, pulls them in tighter. So it'll be more stable with a negative charge than a nitrogen would. So it'll favor the product. Hybridization states, again, this is like asking yourself, does it have pi bonds? And those kind of series of questions. So here, does it have pi bonds? It has one. If it has one pi bond, it needs one p orbital. So it's sp2 hybridized. This nitrogen, this was kind of a tricky question, maybe a bad question. It has, you can see it has one pi bond. It does have a lone pair, but it can't do resonance this way just because the ring is kind of constraining it. So it's really sp2 hybridized. If you wrote sp, that'd be fine. It's a little more nuanced, complicated question than I wanted it to be. It is sp2, but you might not realize the ring strain kind of thing going on. This oxygen has no pi bonds, so you'd think it's sp3, but then you say, well, it has lone pairs. If it has lone pairs, is it one bond away from a p orbital? It is. So it'll want to do resonance. So it'll want to have a p orbital to put his lone pair in. So it's sp2 hybridized. So this is a nice one.
I have a question.
Oh. All right. Let's see. Chairs. Given a chair, do the flip and also do the wedge and dash. Doesn't matter what you do first. Want to recognize the numbering here is arbitrary. It doesn't mean anything. It's just me to keep track of things. OH is equatorial and up. So on the flip, it's going to be up always, right? Up and down don't change. It's going to be up, but axial. All right, so 1 went down, 4 went up. That chair flip. This ethyl was axial up. So on the flip, it's going to be up, but equatorial. Equatorial up. Fluorine is equatorial down. On the flip, it's going to be axial down. Now, like we said, every wedge and dash structure has two different chair structures, right? This wedge and dash structure could be drawn two different ways. So we draw the wedge and dash. I like to think of up as wedged. So OH, ethyl, and fluorine is dashed then. So the OH and the ethyl are both up. Fluorine's going down. More resonance. Add lone pairs. Don't forget to slow down and follow the instructions. Add lone pairs. If I ask for lone pairs, add the lone pairs. All right, bonds broken, bonds formed. All that kind of stuff is happening here. Remember, carbon with a negative charge has a lone pair. Make sure you add those lone pairs in. Don't forget those. Pi bond breaks. The electrons go to one carbon. That has a lone pair now. This carbon lost a bond, so now that's why this carbon only has 3 bonds, right? Because there was an H here. And there's still an H here, and that H never went away, right? Resonance, we never break sigma bonds. And we just kind of move the pi bond, right? Now this carbon has 3 bonds. Move the pi bond again. Now this carbon has 3 bonds. Now we move the lone pair. Now we have this. So why is this the most stable resonance structure? So obviously this isn't a resonance. This is the starting material I got, or the starting thing. So the most favored is this one, because everyone has a full octet, right? Remember we talked about evaluating resonance structures, right? The most important rule for everything, really, the octet rule. Make sure everybody has 8 electrons around them. So I know people will be upset, like, well, the nitrogen has a plus charge. It doesn't want a plus charge. It doesn't matter. Octet rule is more important, right? Everybody wants to have 8 electrons around them. So this is the most important or major resonance form for this molecule, because everyone has a full octet. That's the most important thing. All right, rankings. Make sure you show your rankings. Make sure you write 1, 2, 3, 4, red, white, and blue. Because if you goof up your rankings, you can still earn points. Because whatever your rankings are, if you do the R and S part right, you can still earn points. So make sure you show your work. So here, right, asymmetric centers are sp3 hybridized, bond to 4 different groups of atoms. So here's our center. We go 1 bond out at a time. So first is oxygen, carbon, carbon, carbon. So oxygen is the highest rank there. So you just go 1 bond out at a time. I know there's a bromine there. And a bromine by itself would be oxygen, but there's a carbon in between there. So you go 1 bond out at a time. So oxygen, carbon, carbon, carbon. So oxygen wins. Now we're here, and now it's like, okay, now it's a carbon. We have a bromine there, an H and an H. And here we have a chlorine, an H, and an H. Here we have a carbon, and an H, right? Carbon, carbon, and an H. So now bromine wins, that's 2. Chlorine beats carbon, that's 3. And then this is 4. That's how you do your rankings. You do the red, white, and blue, use your model kit. You should be getting R for this. Over here, it's a little more straightforward. It's just atomic numbers. Iodine is 1, sulfur, 2, phosphorus, 3, 4. Again, get those rankings done. Do your model kit. It should be R. Oops, so I wasn't recording. Wedge and dashed to a chair. I numbered just because to keep track of where things were. So this ethyl's on 3. I want to make sure it's on 3 in the chair, not on 2. I always think the wedges are up, dashes are down. So if I make this 1, I just numbered it. And so, okay, the bromine's wedge, that means it's up. And at carbon 1, if it's up, if I'm calling this carbon 1, the bromine has to be up, it has to be axial, because that's the up position there. So every atom has an up or down position. So the bromine's up, Then on carbon 3, the ethyl I think is down. So on carbon 3, the down position is equatorial. 4, the OH is up. The up position is equatorial. 5, the chlorine is down. The down position is equatorial. So that's what I got there for this one. This isn't the only way you could do this. You could do this lots of different ways. Last one, very similar to quiz 2 a little bit. Here, you see the arrows, looking for the intermediate. Lone pairs, again, make sure you read the instructions, write those lone pairs. I'm going to do it. What are the results of this? You're going to have electrons moving. Oxygen got an extra lone pair. This carbon right here, of course, there's an H there, and it's still there, but it lost a bond, so now we've made a carbocation. So there's a plus charge there. Balance our charges. Lone pairs here. Makes a new pi bond. Pi bond breaks. Makes a pi bond there instead. And again, right, if you looked at these, this is probably the worst resonance structure because, again, it doesn't have a full octet. You can think of that too.